This is part one of the series Applications of Differentiation. And the first topic we're going to talk about is related rates. In many applications, there are multiple quantities that are related by a third common quantity. In our case, that common quantity is going to be time. And we're going to investigate how multiple variables relate to each other with respect to a change in time. And so we're going to deal with equations that define the relationship between those variables as well as the individual equations that tie them together. So let's go ahead and get started and take a look at a problem. In this first problem, it says functions x and y are both differentiable functions of t, that would be time, and are related by the equation y equals x squared plus 3. We're supposed to find what dy dt, that is the rate of change of y with respect to t, when x equals 1, given an initial condition that the rate of change of x with respect to time is equal to 2 when x is 1. And so we're going to have to come up with an expression that has a dx dt and a dy dt. Well, given that this equation is y equals x squared plus 3, what we're going to have to do, since we're looking for rates of change, is differentiate. And since this function is not explicitly defined in terms of t, we're going to be doing an implicit differentiation of y and x with respect to t. So if you remember the discussion on implicit differentiation, then that'll help you. If not, I would suggest going back and checking the videos related to implicit differentiation. So let's go ahead and begin here, and let us differentiate this function implicitly. So the derivative of y with respect to t using Leibniz notation is dy dt. So dy dt equals, this derivative is 2x, and with each variable we're going to have to use the chain rule. So the derivative of the inside is dx dt plus 0, because the derivative of a constant is 0. Now we're looking for dy dt when x is 1, given that dx dt is 0. So let's go ahead and do our substitutions here. So we know that dy dt equals 2 times x is going to be 1 when dx dt is 2. And we can leave the 0 where it is. 2 times 2 is 4, times 1 is just 4. Now, granted, this was a fairly trivial example, but it gives you an idea of how the rates of change of two variables are related by a third variable, in this case time. So let's go ahead and try another example. So in this example, a pebble is dropped into a calm pond, causing ripples in the form of concentric circles, that is, circles with a common center. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Now, one of the keys to solving these kinds of problems is we need to characterize what we're given and what it is that we're trying to find, and try to put it in terms of the problem situation. So here, the radius of the outer ripple is increasing. Well, radius is increasing, so that's a rate of change of the radius with respect to time. So what they're giving us is dr dt is 1 when the radius is 4. So when r equals 4. Then what we're looking for is the rate of the total area of the disturbed water changing. Well, up here it said that the ripples are in the form of concentric circles. So we're actually looking for the area of a circle. So area is going to be pi r squared. And we're looking for dA dt, excuse me. So we're looking for dA dt. The rate of change of area with respect to time when the radius is 4. So what that means is we're going to differentiate this equation, area and radius, with respect to time. So let's go ahead and do that. So dA dt, that's the derivative of a with respect to time, equals, well, this is just a constant. Pi is a constant, so using the constant rule, I'm going to pull out the constant, times 2r, that's the derivative of r squared, dr dt, implicitly differentiating this expression in terms of time. So now we'll go ahead and do our substitutions. Here we have dr dt is 1, so that'll go in here, and r is 4, that'll go in here. So dA dt is going to equal pi times 2 times 4 times dr dt, which is 1. So this is 8 pi. So we know that dA dt equals 8 pi. And since the radius is given in feet and the time is in foot per second, this is square feet per second. So not too difficult of an example. Let's go ahead and look at a third one. So in this problem, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. We're to find the rate of change of the radius when the radius is 2 feet. So air going into a balloon, we're talking about volume. And the volume is going to be the volume of a sphere. So we're dealing with the volume of a sphere. So let's write down the equation of volume of a sphere. That's 4 thirds pi r cubed. And it's 4.5 cubic feet per minute. So we know that dV dt, that's the rate of change of volume per unit time, is 4.5 cubic feet per minute. Okay. Now we're supposed to find the rate of change of radius. So we're looking for dr dt when r equals 2 feet. So clearly we have to differentiate this because the derivative of v is dv dt, so we're looking for the derivative of this guy. So let's go ahead and do that. So dv dt, that is the derivative of v with respect to time, implicitly differentiating volume with respect to time, equals, again we have a constant of 4 pi over 3, so let's pull that out. 4 pi over 3 times the derivative of r cubed is 3r squared dr dt. Again, differentiating r with respect to time. Well, here we have a simplification. The 3's go away. So dv dt equals 4 pi r squared dr dt. Okay, now we take our values that we substitute in. Our r is 2, so that's going to go in here. And we're given dv dt is 4.5, which is going to go here. So we have 4.5 equals 4 pi 2 squared dr dt. So we're going to have to solve this expression for dr dt. So let's go ahead and do that over here. So we have 4.5 divided by this entire quantity, because we've got to get drdt by itself. So basic algebra here, 4 pi 4 equals dr dt. So putting this into our calculator, we see that dr dt equals 0.0895, and since radius is a linear measurement, that's going to be feet per minute. Okay, let's go on to another example.